Okay, let's resume the class. Okay. So we are going to talk about recurrence relation. So let's take a look at this sequence. Okay, so we start with 1, and then 3, and then 9, and then 27, 81, 243. As you may guess, what I'm trying to write down is I want to list out all the powers of 3. And then we want to describe my sequence. So the first way is I may just write down, okay, so let's call the first term A0, A1, A2, A3. So I may just write down AN is equal to, so this is going to be a sequence of A, so it is equal to 3 to the power n. So this is one way to describe this whole thing. And then we may actually write down where n, we consider n is equal to 0, 1, 2, 3, and so on and so forth. So they are all integers starting from 0. Okay, then in that case, I can find out what is A0. A0 is equal to 3 to the power 0, so I get 1. A1, I get 3 to the power 1. A2, I get 3 to the power 2, and so on and so forth. So this is one way. Alternatively, I may write down a different way. So I may try to specify what is the value of A0. So A0 is equal to 1, that we know. And then I can talk about what is the relationship between the terms here. So if you look at it, so if I start with AN, then it is always equal to 3 times AN minus 1. For any n equal to 1, 2, 3, 4, and so on and so forth. Is that okay? So what is the difference between these two things? For method 1, for the first part, if I know the value of n, then I can quickly or exactly compute what is the value of this AN. So if I have n is equal to 7, then I just know that I want to get 3 to the power 7 and get it done. Is that okay? And then we call this one, this is called the closed form for AN. So closed form is, if you just tell me the value of n, I have an equation, I have a formula to compute the value of AN. Okay? Now for method 2 here, this is rather different. I give you a value of A0, a certain particular value of the sequence. And then I tell you the relationship between the terms. Actually here, the relationship between adjacent terms in the sequence. Now, method 2 is also precise because if I start with A0 and then using this relationship, I can get the value of A1. And after that, I get the value of A1. I can further apply this relationship again to get the value of A2, and so on and so forth. So eventually, if I want to compute what is A7, then I can apply this again and again and again and again. And I must be able to compute the value of A7. Exactly to be the same result as this one. Is that okay? So this one is not closed form because if I just give you the value of n, you cannot exactly compute using a single formula what is the value of AN. But on the other hand, you still can solve it. So this way, the second method, like this, we call this a recurrence relation. So this is the name. Recurrence relation. So which tells the relationship of a term with the other terms in the sequence. Usually, so recurring means it happens in the past. So usually, we are focusing on what is the value of AN in terms of the values of AN minus 1, AN minus 2, AN minus 3 up to A0 that happens in the past. So with this relationship, together with this, we usually call it a boundary condition or an initial condition. So we call it a boundary condition. Sometimes we may have more conditions, more values of the terms in the sequence conditions. Then this is usually a single relation, usually. Then we can still define your sequence precisely without any problem. Okay. Now, of course, what is the best? Which one is better? Closed form is better or recurrence relation is better? Which one is better? Well, it depends, but usually closed form is better because we are more interested in talking about getting the value of an quickly. Okay. But of course, recurrence relation is also useful, okay, for two reasons. One is the closed form may be very difficult to find at the beginning. So recurrence relation, actually, if you can derive a certain recurrence relation for things, at least you can solve the problem. I can still solve A7. Just it takes time. If you write a computer program, it just takes 7 loops, rather than it takes constant time to get the value here. Okay? So getting a recurrence relation still solves the problem. Okay? You still can find an. The second thing is a recurrence relation also captures the property between the terms. Okay? So this tells us more information about the structure of the terms inside the sequence, or the structure of the numbers that you are counting. What is the relationship between the case where it is case n or case n minus 1? Okay, so this is, if you just have a single formula, you have no way to tell what is the relationship between adjacent terms. But for recurrence relationship, it gives you more information in terms of that. So if you want to show other things that is relying on the properties, then a recurrence relation is good. But on the other hand, if you just are interested in the value, then of course a closed form will be better. Okay, and the focus of this lecture is to give you a problem, derive. So we need to do 2 things: derive a recurrence relation for that, and then try to find out what is the corresponding closed form of the term. Okay, so this is the target of this class. Okay. So let's start with an example. So this example is this one. So let's suppose that we have n ovals. So ovals like this. So this is the case where we have 2 ovals. And then, so let's define an to be the number of regions that the plane is divided by n ovals such that what? Such that any 2 ovals any 2 of them intersect at 2 points. So this is one thing, and no 3 of them intersect at the same point. No 3 ovals intersect at the same point. Okay, so let's figure out what does it mean. So let's say this is the case of n is equal to 2. And then we have this oval 1 and then this oval 2, right? And then these two oval intersect at this one point and the second point. Okay, it's good, it fits, okay. And then we are interested in how many regions the plane is divided into. So we have region 1, which is the outer region. We have region 2, which is this part. Is that okay? Region 3, which is this part, and then this is region 4. Is that okay? So what do we have? We have A4. So let's have blue. Okay. So let's write down. So what do we have? So we now have, so A1 is equal to what? I don't know. Let's compute. And then A2, what is A2? A2 is equal to 4. Is that okay? Okay. So what is A1? A1, you just have a single oval, right? How many? 2. Good. 2. How about A3? A3, so let's do it more. So A3. So let's have n is equal to 3. Okay. So oval need not be to be of the same shape as long as they are oval. So okay, so let's have a third oval like this. Make it into oval. Okay. So how many regions are there? Let's count it again. So we have 1 outside, and then we have 2 here, 3 here. Is that okay? And then what else? 4, 5, 6, 7, 8. Is that okay? So A3 is equal to 8. And then what is A4? What do you think? 16, you guess, right? 16. Okay, let's try. Okay. So we get a fourth oval. Okay, this time let's have a black oval just to make sure that we are intersecting every oval here. So let's have a fourth oval there. Looks like this. Is that okay? Okay. Oh, let's do counting. Well, yeah, we are intersecting every oval at 2 points, right? This one intersect these two at 2 points, intersect these two at 2 points, intersect these two at these 2 points. Is that okay? So it fits. Okay, so let's have 1. Wait, this is not good. Let's have 1 again. 1, 2, 3, 4, 5, okay, 6, 7, 8, 9, 10, 11. Is that okay? So far so good, right? 12, 13, 14. Oh, that's it. That's just 14 of them. Okay, so originally we thought that it is going to be 16, but no, this is not like a 2 power. It's like 14. Okay, so intuitively, let's think about it. So should the number of regions grow exponentially, or should it be growing like in what way? Exponentially, like 2 powers, it means what? It means that for my new oval, whenever I add a new oval, this new oval can cut each of the existing region into 2 parts. Then I get double, right? Well, it doesn't look like so because if you look at it, if I'm cutting these few things, then I cannot cut this part, right? So some parts you cannot cut it. Okay. Actually, how to determine the number of parts that it cuts? Actually, it determines in what? It determines by the number of intersection points here. Because if you look at it, this is one intersection point, this is another intersection point. It is cutting this originally one single region into two parts. Is that okay? So you add one because of this segment. Is that okay? And then you have the next pair of intersection points, these two intersection points. Is that okay? And then this new segment is cutting the original region into two parts. Is that okay? And then the next one is this new segment. This new segment is cutting this original piece of region into two, from one into two. So what does that mean? So this new segment cut this part. This new segment cut this part. This new segment cuts the whole original 1 into 1 and 14. Does that make sense? So what does it mean? So if we know how many segments are there, then we know how many regions will be added. If I have one segment, I'm adding one region. If I have two segments, I'm adding two regions. If I have k segments, I'm adding k regions. Is that okay? Okay, let's look at the simplest case. Let's look at the simplest case. Originally, we have just two regions, am I correct? 1 and 2. Now, let's add one oval. If I add one oval here, this new oval, the circumference of this oval will create 1 and 2 segments, am I correct? This segment will make this whole piece from 1 into 2. It adds one extra region due to this segment. Is that okay? And this next segment adds one region, because originally it is just a whole outer region, but now it adds one more region. Is that okay? So each segment here, 1 and 2, two segments add two regions in total. Is that okay? Now, let's add another oval. This time, let's add an oval like this. Okay. This segment divides this into two. 1, 2. Is that okay? So it adds one region. Originally, just one single region. Now it is counted as one region and the second region, two regions. Is that okay? And then this new segment here, from this point to this point, it makes this region from 1 into 2. It adds one more. This segment adds one more. This segment adds one more. Is that okay? And because of how many segments are there? 1, 2, 3, 4. 4 segments, then we're adding 4. So we add 4. So previously, start with 2, you add 2, you get 4. And now you have 4, you add 4, you get 8. Is that okay? And then one more. So let's look at the blue one. Oh, the blue one. Let's make it like this. Okay, it looks like this. So it is like this. So it is still oval. Okay. Okay. So we have how many segments are there? 1, 2, 3, 4, 5, 6. Is that okay? So there are 6 segments here. Then we are going to add 6. 8, you add 6, it becomes 14. Okay. So how about this? Suppose that I have an minus 1. So this is the value of an minus 1. And then I want to get an. Then I should find out how many new segments will be created by adding the nth oval. How many segments are there? How many segments are there? Segments comes from intersection points, right? I have 1, 2, 3, 4, 5, 6. 6 intersection points on a circle or on an oval. Then I have 6 segments, right? So when I add the nth oval, how many intersection points will I be adding? How many intersection points? 2 times n minus 1. Because you recall that each oval cuts the other oval in exactly 2 locations. So the last oval, when you add it, it is crossing the first oval in 2 places, the second oval in 2 places, up to the n minus 1 oval in 2 places. So we should be adding 2 times n minus 1. Okay, so this is a recurrence relation for this problem. And then we can add the boundary condition. Let's say A1 is equal to 2. Then the whole thing together, combined together, will allow us to compute A100, A200, whatever that we want. Is that okay? And then just from this example, if we need to guess, how does AN grow? Is it like, so it doesn't look like exponential, right? Each time you add, so the first time it is like you add 2, the next time 4, the next time 6, and then 8, and then 10, and then 12. So how does it grow? It grows quadratic. Is that okay? Good, excellent. So this is the recurrence. And then let's see how we can solve it. Okay? Okay. Okay, so recurrence, there are many types of recurrence relationships, but then some types are very easy to solve, and then we will look at those first. The first type that we are going to look at is called linear recurrence. So we have the first type called linear recurrence. Okay, so how does a linear recurrence look like? So a linear recurrence looks like this. So you have start with some term an. You may start with some term an, and then you can express an as some number, let's say C0. Or usually, you use C1. C1 times an minus 1 plus C2 times an minus 2 plus dot 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 up to ck times an minus k. Okay, where all the CIs are constants. So if a recurrence looks like this form, so an, let's say an is equal to 2 times an minus 1 plus 3 times an minus 2 plus 1 times an minus 3, something like this, then it is called a linear recurrence. Is that okay? So linear in the sense that each thing here is just a single a. You are not having an minus 1 square. So that is not linear, that is quadratic. Is that okay? So linear means that everything is just level 1. an to the power 1, an minus 2 to the power 1, something like this. Is that okay? You don't have an minus 1 times an minus 2. So that would be quadratic. Okay? And then all these are just simple constants. Okay? If a recurrence is of this form, then it is called a linear recurrence. Okay? Now, if I have a linear recurrence of this form, then, okay, so this is a linear recurrence of degree k. So, or degree k minus 1, k plus 1, or whatever. So here, for this one, what does it mean? So if I have the value of A0, A1, A2, up to, so how many terms are there? There are k terms here. Let's say A, k minus 1, okay. Now, if I have the terms A0, A1, A2, AK minus 1 defined, they are given, then I can use these terms to plug it into the equation and then get the value of AK. Does that make sense? Because I now have A0, A1, A2, A3 up to AK minus 1. Look at it. There are k terms here. 1, 2, 3, up to. So n minus 1, the first term, n minus 2, the second term. So n minus k will be the kth term, right? So if I have k consecutive terms given, then I will have the next term computed. Is that okay? So if I give you the value of A0, A1, A2, sorry, dot, 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 up to AK minus 1, so there are k terms given, then I can use them to compute what is the value of AK. Does that make sense? Okay? And then if I have the value of AK known, then I have A1, A2, AK minus 1 up to AK, so I can get AK plus 1. Is that okay? And so on and so forth. Then in that case, I can get every terms that we want. Okay? Okay? So here, yeah, if my memory is correct, so let me just call this a linear recurrence of degree k, because whenever I fill in k values here, then I have the k plus 1 value. Okay? Yeah. Okay? So if you look at that, sorry, this is even a simpler linear recurrence. Sorry. I can actually make a linear recurrence a little bit more complicated. So this is just the relationship between the terms that happens in the past. I can actually even add a certain function fn here that just depends on the value of n. This is still called a linear recurrence. Is that okay? So the linear, what is a linear recurrence? A linear recurrence is the relationship of an with the previous terms in such a way that for each previous term that appear, it is just of a single degree, degree 1. So that's why linear. But you have the option to have a certain function that relates just on n added here. Is that okay? So all the discussion still applies. So if I give you the value of A0, A1, A2 up to AK minus 1, then I will still be able to compute AK. Is that okay? Does that make sense? Because I have all the terms here, so I know what is the value of this one. I plug in the value of k here, I will know the value of fk. Then I have the whole terms, each term on the right-hand side evaluated. So I will get AK. Is that okay? Okay, so this is a very general way. Let's look at a simple example.